Okay, hi everyone. Thanks for joining the Protocol Labs Research Seminar Series. Today's speaker is Dr. Shaileshh Bojja Venkatakrishnan. Shaileshh is currently an assistant professor in the Computer Science and Engineering Department at The Ohio State University. Prior to this, he was a postdoc in the Networks and Mobile Systems group at MIT, where he worked on problems at the intersection of network systems, algorithms, and theory. He is interested in fundamental algorithmic questions at the networking layer of Bitcoin and other cryptocurrency networks, as well as the application of machine learning for learning algorithms over networks. Other topics he has worked on include scheduling algorithms for data center networks, peer-to-peer networks, and information theory. He received his PhD from the University of Illinois, Urbana-Champaign in 2017, where he was a recipient of the Joan and Lalit Bal Fellowship. He is also a co-recipient of a grant from Protocol Labs Research and the Resilient Networks Lab to address scalability bounds of peer-to-peer pub-sub networks. Dr. Venkatakrishnan, the virtual floor is yours. Take it away.
Thanks, Jonathan, for the introduction, and also thank you for inviting me here. So in today's talk, I'll be presenting some interesting ideas on how to make the peer-to-peer network in blockchain systems more efficient. Oops. Okay, so blockchains, they are a technology for maintaining a Byzantine fault-tolerant public ledger of transactions across nodes in a peer-to-peer network. Compared to ledgers that are based on more classical consensus protocols, a key difference with blockchains is that there is no central permissioning authority that controls participation of nodes in the network. Instead, permissioning here is mediated by resource. For example, in proof of work, it's the amount of compute or the hash power that a node has, which decides participation of a node in the network. And this protects against Sybil attacks. Now, since the introduction of Bitcoin in 2008, a number of other cryptocurrencies have been developed, and today the market capitalization stands at more than $300 billion. In addition, there's also decentralized applications or dApps that are increasingly being developed based on the blockchain technology. And these dApps, they strive to remove any digital intermediaries, such as like a middleman that's standing between a seller and a customer, for example. And more established companies such as IBM and Facebook, they're also increasingly investing on blockchain systems. So this is really a very exciting space, but a key problem facing blockchain systems today is scalability. For example, in Bitcoin, it can support a maximum of 10 transactions per second, which is in stark contrast to more established payment systems like Visa that can support more than 1,700 transactions per second. The transaction fees in Bitcoin can also be pretty high, and each node in Bitcoin has to store the entire blockchain that can be several hundred gigabytes in size, and it can only get bigger from here. And lastly, it takes more than an hour to confirm every single transactions in Bitcoin compared to just a few seconds that it's going to take in Visa. Well, each of these aspects is an important problem that needs to be addressed. In this talk, I'll primarily be focusing on improving the confirmation latency of transactions in general blockchain systems. In general, we can think of a blockchain as being comprised of the following 4 layers. At the bottom, we have the peer-to-peer layer, whose job it is to broadcast messages, and these could be transactions or blocks, to all the nodes in the network. Above this, we have the consensus layer, excuse me, whose job it is to ensure that nodes agree on the exact sequence of transactions in the blockchain. And above this layer, we have the sharding layer. And sharding is basically, we divide the blockchain into smaller pieces for scalability reasons, so that each individual node has to only maintain a small portion of the blockchain instead of downloading the entire blockchain that can be big in size. And at the very top, we have the application layer, which includes payments, gaming, things like that. And across each of these 4 layers, researchers have put forth proposals to improve the scalability and efficiency. For example, in the peer-to-peer layer, there have been proposals to compress and code blocks to ensure that they spread very fast. And there's been a huge amount of work in designing more efficient consensus protocols. And there's also a lot of work in sharding protocols. And finally, at the application level, there have been off-chain solutions such as the Lightning Network or the Raiden Network that promise a much faster rate of transactions and a lower confirmation latency compared to on-chain payments. Now, because the peer-to-peer layer is so fundamental to all of these other layers, in today's talk, I'll be focusing on how to make the peer-to-peer layer more efficient. So what does efficiency mean in the context of a blockchain system? It basically means messages such as blocks and transactions, they need to propagate through the network as fast as possible. And we can improve the efficiency of in the peer-to-peer layer through several different ways. For example, we could compress and code blocks. Essentially, we could reduce the size of the message itself so that the messages propagate fast. We could change the gossip protocol that nodes use to relay the message to their neighbors. We could change the transport layer protocol used to communicate the messages. For example, instead of using TCP, we can use UDP with some error correction. Or we could change the routing to, we could do something like cut-through routing, where instead of downloading a block in its entirety before forwarding it to your neighbor, you immediately start forwarding a block once you receive even just a small portion of it. And indeed, all of these approaches, they have been proposed in the literature. But in today's talk, I'll focus on an aspect that's fundamental to all of these proposals, namely the peer-to-peer topology, or how different nodes should be interconnected in the blockchain network. For concreteness, I'll be focusing on a specific blockchain system, namely Bitcoin. So in Bitcoin, as transactions are generated, they are consolidated into blocks using the longest chain protocol. And when a miner mines a block, he then broadcasts the block through the network. There is no sharding in Bitcoin. And the goal for us is to design the topology of this Bitcoin network such that the block gets propagated to all other nodes as fast as possible. Today, Bitcoin follows a random topology. That is, a node in Bitcoin, it connects to 8 random neighbors from among the set of IP addresses that it knows. And a node also accepts a maximum of 125 incoming connection requests. However, the random topology can be very inefficient. For example, if a block is mined in New York and it's sent across the world, then the block could actually zigzag across continents as shown by this path before reaching a destination, for instance, in Tokyo. Instead, we would have liked if the block took a much more direct path between New York and Tokyo in order to have a smaller latency. So we can ask this question, how inefficient is the random topology? And towards the end of the talk, I'll give some numbers from our experiments. But first, let's try to understand this inefficiency from a theoretical point of view. And for this, I'm going to be using a line of results from the network systems community which say that nodes on the internet can be embedded or mapped onto a metric space such that the point-to-point latency between any two nodes on the internet, it corresponds to the distance between the two nodes on this metric space. For example, you can think of this metric space as a hypercube, as a unit d-dimensional hypercube. And what we are saying is, if we measure the round trip time of sending packets from New York to Tokyo, it corresponds to the Euclidean distance between the New York point and the Tokyo point in this metric space. Okay. Now let's use this model to generate a theoretical model that we can then use to analyze this random topology. So we're going to be considering a d-dimensional unit hypercube, and let's choose some endpoints uniformly at random from this hypercube. Now, these endpoints are going to denote the n nodes in our network. And in this model, the distance between any two points in this picture, it denotes the time it takes to send a message from the first point to the second point. Okay. So we can also think of this square as the globe, if you wish. Next, we are going to interconnect these points randomly. That is, each point is going to choose some log n neighbors uniformly at random. So basically, this is like an Erdős-Rényi graph, but one that is embedded onto a metric space. Now, once we have this model, we can, it's a very simple model. We can ask the following question. So if we take 2 points in this picture, we can ask by how much does the shortest path distance from x to y on this random topology exceed the geodesic shortest path, or the physical shortest path from x to y. So the black path shown here is the shortest path from x to y on this random topology. And this pink line here is basically just a straight line connecting x and y. And we can ask the question, by how much does the black path length exceed the length of the pink line? And in fact, this precise question has been studied before. And due to a result by Fries et al., it shows that the shortest path on this random topology, it exceeds the geodesic shortest path by a logarithmic factor. Okay. So a natural question now is, can we improve upon this? Can we close in this logarithmic gap? Okay. And the answer here is S. And this is due to a topology called the random geometric graph. So this is the same picture as before. So you have a hypercube, and then you're drawing points, and you have drawn points randomly. Now the way we would construct a random geometric graph is, for each point, we would first consider a ball of a certain radius r around the point. And r is just a parameter of the algorithm. And the node is going to be connecting to every other node that falls within this ball. Okay. And if the radius parameter is not too large, then the degree of each node is also not going to be large, and we are okay. Now with this random geometric graph, we can ask the same question. By how much do the shortest paths on the random geometric graph exceed the geodesic shortest path? So as shown in this picture here on the right-hand side, turns out this gap is actually pretty tight. The shortest paths on this random geometric graph, they are aligned very closely with the geodesic, or the physical shortest path from x to y. So there's only a constant factor gap in the Euclidean distance versus the graph distance. Now, one observation here is that in this random geometric graph, like the number of hops in this path, it seems to be a lot. And that is because in this model, we have only modeled link latencies. We've not really modeled node latencies. But I'll come back to this point later on. Now, while the random geometric graph is very efficient on our toy model, in practice, this problem is much more complicated. In addition to heterogeneities in link latencies, there's also heterogeneities in link bandwidth, which affects the time taken by messages to propagate through the network. Nodes also have varying mining or processing power, which affects the time it takes for a node to verify a block before relaying it to its neighbors. The density of nodes in different parts of the world can also vary a lot. So even if we were to implement a random geometric graph in practice, it's unclear what R parameter to choose for the algorithm. And lastly, the network conditions can vary. So there could be link failures, router failures, network congestion, which could essentially change the point-to-point latency between two nodes over time. So all of these heterogeneities make finding an efficient peer-to-peer overlay a very non-trivial problem. So I must mention here that designing efficient overlays for peer-to-peer networks, it's a very well-studied topic. There's been more than 20 years of research here. And this really interesting structured solutions like CORD, Cadamlia, and Pastry, and also unstructured solutions that have been proposed in the past. Some of these solutions do take into account the geographic proximity of nodes while deciding the topology, but they don't really look at all the heterogeneities that I spoke about in the previous slide. So in this presentation, in our work, we present Perigee, which is a decentralized overlay construction algorithm that decides neighbors for a node based on the node's past interactions with them. So the high level idea is very simple. So a node basically starts off with an arbitrary set of neighbors, and it's going to observe how fast each neighbor relays blocks to it. And based on that history of observations, it's going to decide which subset of neighbors to retain and which subset of neighbors to disconnect from. And additionally, it's also going to periodically make connections to random neighbors as a way of discovering potentially new unseen neighbors with potentially very good connectivity to the rest of the network. And this process is going to repeat. Okay, so I'll explain the algorithm in more detail in just a few minutes. But so our protocol is motivated by the multi-armed bandit problem. So here a node essentially wants to connect to some set of neighbors that can relay blocks fast to it. So we think of the different possible sets of neighbors a node can connect to as the different arms in this multi-armed bandit problem. And a node essentially wants to connect to that set of neighbors that relay blocks very fast, but a priori it does not know which set of neighbors are going to be relaying blocks how fast. So it's really like trying to explore different candidate sets of neighbors and trying to converge onto the best set of neighbors as fast as possible in order to minimize the opportunity cost or the regret, as it's called in the multi-armed bandit literature. Our algorithm automatically adapts to network heterogeneities, such as in hash power, latency, bandwidth, or any other type of heterogeneity. And we show through simulations that our protocol is 30 to 40% faster compared to the random topology. So just to give a sneak peek of the algorithm, so we run Perigee on the toy example that I talked about before. And as you can see here on the topology that Perigee finds, the shortest path between the 2 points x and y is much closer to the geodesic shortest path from x to y. But that's not the only thing. Even if we were to change the network conditions, for example, supposing I introduce some node delays into this toy example. So in addition to link delay, each time a message reaches a node, it's also going to incur some node delay. Even then, the perigee adapts to this setting, and in the topology that it finds, the shortest path is still much better. It's still much better compared to the shortest path that we see on this random topology. So just on the star example, we can get a flavor for, like, even if the network settings change, Perigee is able to automatically adapt to it and find an efficient topology. So this is the network model that I'll be considering for both to explain the protocol and also for our experiments. So I'm going to assume that blocks are mined in rounds. So in each round, there's going to be one node in the network that generates a block, and it broadcasts the block to everyone else in the network. And the probability that a node mines a block in a round is proportional to its hash power. So for each node B, there is a hash power h of V. When a block is mined by a node, it's immediately sent broadcast to its neighbors. And when a block traverses a link UV, it incurs a latency of L of UV. And when a block actually reaches a relaying node, it incurs an additional node processing delay of D of U for a node U, after which the block is forwarded to the relay node's neighbors. And this process continues till the block is spread to all the nodes in the network. And that completes like one round. And in the next round, a new node is going to mine a fresh block, and so on. We're going to assume that nodes have a fixed degree bound. And for simplicity, I'm also going to assume that each node knows the IP address of all the other nodes in the network. So essentially, it can connect to any node in the network that it wants to. So with this setting, the question now is, how can we design a topology that minimizes the time it takes for messages to reach 90% of the hash power in the network? So essentially, when a block is mined, we want to deliver the block as fast as possible to the other miners. And this objective is slightly different from minimizing the time it takes for the block to reach 90% of the other nodes in the network, because in general, hash power need not be uniformly distributed across nodes. For example, in this toy picture here, just these three nodes have 90% of the hash power in the network. And in this case, we would really be interested in having good connectivity just to these three nodes, and we really don't care about the other nodes in the network. Okay. So here's the protocol. Now, supposing the degree bound is 4, meaning each node is interested in selecting 4 good neighbors, and we are going to be focusing on this node B here. So B starts off with an arbitrary set of 4 neighbors as shown in this picture. Now, based on how each of these 4 neighbors, they are relaying, based on how fast these 4 neighbors are relaying blocks to B, B is going to be assigning a score to different subsets of neighbors. So neighbor 1, 2, and 3 gets is assigned a score. Neighbor 2, 3, and 4 is assigned a score, and so on and so forth. Now, in general, if you have a degree bound, the size of the subset, we would choose it something like 70 or 80% of your degree bound. For example, if you have 10 neighbors, if your degree bound is 10, then for each subset of 7 or 8 neighbors, we would be assigning a score. Now, once this score has been assigned, in the next step, B is going to retain that subset of neighbors having the best score, and it's going to disconnect from the others. In order to maintain this degree bound, it's going to, like, it disconnected from some neighbors. Instead, it's going to randomly pick some other neighbors, and it's going to form connections to them. Okay. And this process is going to continue periodically. Now, the reason that we assign scores to subsets of neighbors and not to individual neighbors is because a node V really only cares about receiving blocks fast from its neighbors. It doesn't care which of the neighbor forwards the block to it. For example, so in this picture here, the node on the top can have a very good connectivity to just 30% of the network, and it could have terrible connectivity to the rest of the network. The yellow node can have, or the green node can have good connectivity to a different 30% of the network, and it could have terrible connectivity to the others, and so on. But if you look at these three nodes together as a group, they cover like 90% of the network, and regardless of where the block is mined, it's going to reach V in a very fast way, right? So this is why we want to be assigning scores to groups of neighbors and not just to individual neighbors. Now, this way of choosing the neighborhood set by assigning scores to different peers, it's not a new idea. There's like several works that do this, but the key difference here is in prior works, this score function is typically handcrafted, meaning the network designer, he carefully designs the scoring function as a function of, for example, the round trip time, the bandwidth, or any other feature that he may know of his neighbor. And these are usually very well thought of and carefully handcrafted scoring functions. Whereas in our case, we don't handcraft the scoring function. Instead, we design a scoring function that is directly matched to the objective that we are trying to optimize. So for example, let's look at this picture here. So there's node V again that's interested in scoring this group of neighbors highlighted in red. Now for simplicity, let's assume that this node V knows the precise time when different blocks are mined in the network, let's say. Then node V basically, as these blocks are mined and as these blocks are being relayed to V by this group of neighbors, V knows the precise total delay it takes for these blocks since they were mined and since the blocks were relayed by this group of neighbors. Okay. So we can now use this delay information to compute a histogram where basically for different blocks, it knows the delay incurred, and therefore it can just compute a histogram of these delays. And if V chooses the 90th percentile in this histogram as the score function for this group of nodes, then we can see that that is basically the objective that we wanted to optimize in the first place, right? By essentially choosing the score to be exactly the objective that we want to optimize for, we would be steering V to choose that subset of neighbors for whom this 90th percentile delay is the lowest possible. Okay. And also this type of a scoring method is also very robust to heterogeneities in the network. So there could be differing link latencies, differing bandwidth, or any other heterogeneity in the network, but we really don't care about any of that, because ultimately the only thing that we care about is how fast does this group of neighbors relay blocks to me. Okay. So this is all good, but in practice, V does not know when each block was actually mined, and therefore V has to have some type of an estimation mechanism to estimate that. And in the next few slides, let's look at how we actually implement this. Okay. So this is V again, and it has 4 neighbors. And for each block that has been mined and that's been sent to V, V is going to only know the absolute timestamp of when it received the block from each of its neighbors. Now in practice, it's possible that some neighbors don't really forward the block to V, or they only forward an advertisement of the block and so on. But for simplicity, let's assume that every block is forwarded to V from all of its neighbors. And there's some notation here that I'm going to be using for the next few slides. So T would denote the absolute timestamp of when the block was received by V. The superscript here denotes the block index. So this is block 1. So this is the superscript is 1. And the subscript denotes the neighbor index. So this is the timestamp for neighbor 1, neighbor 2, neighbor 3, and neighbor 4. Now, using this absolute timestamps of when different blocks arrive, we create a table. The columns of the table are basically the different subsets. So subset 1, 2, 3, 1, 3, 4, and so on and so forth. And the rows of this table are the different blocks. So each time the node receives a block, it's going to be recording when this particular subset, when this particular group of neighbors first relate the block to V. So for example, if I look at neighbors 1, 2, and 3, the first time that we received this block from this group of nodes as a whole is simply the min of these 3 timestamps. Okay, so T1, T2, and T3, the minimum of these 3 quantities is the first time that we received the block from this group of neighbors. And similarly for all the other groups. And as different blocks are mined and as different blocks are being relayed to V is going to record these absolute timestamps. And it's essentially going to be constructing the table as follows. Now here you can think of K as something like 100 or 200. So once this table has been populated, we then convert this table of absolute timestamps into a table of relative timestamps. And the way that we do that is we look at, for each block, we look at the time when the block was first, when the time the block first arrived at V, namely the min of this quantity here. So for the ith block, min of T1, T2, T3, T4 is the first time the ith block was received by V from its neighbors. And we are going to subtract this quantity to all of the entries in our table. So this isn't quite an estimate of the delay it takes since the block was mined to since the block was delivered to V by the particular group of neighbors. But on the other hand, it allows us to compare the relative speed with which these different subsets of neighbors, they forward the block to V. Okay. So once, and notice now these are all normalized timestamps. These are not absolute timestamps anymore. And once we have this new table, the score function for a particular subset of neighbors is simply the 90th percentile of that column. Okay. Now, so this is the algorithm, and this basically, once we have the score, we are then going to do what I described before. We are going to retain the good neighbors, and then we are going to disconnect from the bad ones, and we are going to connect to additional neighbors for exploration, and so on. Now, one issue with this subset, with scoring different subsets of neighbors, is that the number of subsets can be really large if your degree bound is large. So we also considered scoring each neighbor individually in the paper, but in our experiments, we found that scoring subsets of neighbors has a better performance than scoring neighbors individually. But the process here is exactly the same as before. Now, with multi-arm bandit problems, a good algorithm has to balance exploration and exploitation. So what do I mean by that? Now, if we consider an algorithm in which the neighbors are chosen randomly all the time, so this is like an algorithm that is 100% exploration without any exploitation. Whereas if we consider an algorithm where you choose a good set of neighbors based on your prior interactions, and then you just stick to that set of neighbors and you don't change at all, then that's like a greedy algorithm that's 100% exploitation without any exploration. But we know, like from the literature on this multi-arm bandit problem, that if we want to minimize the regret, if you want to minimize the opportunity cost, like a good algorithm has to not only exploit based on its prior observations, it also needs to continuously explore new unseen options as well. So there has to be a balance. And there's this algorithm called UCB, upper confidence bound algorithm, which is a very popular algorithm for efficiently balancing this exploration and exploitation in the multi-armed bandit problem. And in our case, since the objective is to minimize the latency, we actually have this lower confidence bound algorithm. So the idea here is as follows. Now we have collected these timestamps, but these timestamps, they are going to be noisy because of randomness in the mining process, and because of randomness in the topology in the other part of the network, and so on. And therefore, this is essentially noisy data. So instead of simply using the 90th percentile of this noisy data as the score for the subset, we can essentially also compute like a confidence bound based on this noisy data, and use this lower confidence bound as the score for that particular subset. So intuitively, what this is saying is you could have a group of neighbors that are really well connected to the rest of the network, but due to some randomness, they have a poor 90th percentile score. So if we simply consider this 90th percentile score, we would disconnect from that subset of neighbors, and then we would move on to a different set of neighbors. Whereas by giving these neighbors the benefit of doubt, if we add this lower confidence bound, we would retain that subset of neighbors just for a few more rounds, and we would gain more confidence in their 90th percentile delay before really deciding on whether to retain them or whether to disconnect and then move on. So for more details, I'll refer you to the paper. So let me describe our experimental setup and results in like the next few slides. So we built like a Python-based simulator to evaluate Perigee and also other protocols. So we consider a network of 1,000 nodes from the BitNodes data set, and the latency between any pair of nodes in the set, it depends on the geographical location of these two nodes, and we get that from the iPlane data set. And each node has a node processing delay, and nodes also have a hash power that's sampled from some exponential distribution. As baselines, we compare Perigee against the random topology, against Kademlia, against a geographic-based topology. So the geographic-based topology is each node makes half of its connections to other nodes within the same continent, and it makes half of its connections to nodes that are in different continents. And also the complete graph, which is every node is connected to every other node, and this is like a theoretical lower bound. So here are the results. The x-axis here shows node index. So there are 1,000 nodes in the network, so 0 to 1,000 or 999. And the y-axis here is for each node, we measure the smallest time it takes for to reach 90% of the hash power in the network, and that's the y-axis. And so here there's a curve that shows the performance of the random topology. And we can see that for 90% of the nodes, it takes like 500 milliseconds to reach 90% of the hash power in the network. And in the other extreme, we have the complete graph. Everyone's connected to everyone, and this takes about 200 milliseconds. And Perigee, on the other hand, it takes roughly 300 milliseconds, which is like 30–40% better compared to random. Now, Kademlia is a structured solution, but it's also again not going to be looking at geography of the nodes, so its performance is similar to random. Whereas this geographical algorithm, even though it considers geography in some sense, it's only slightly better compared to the random algorithm. Now, one important line of work in trying to accelerate the speed of block propagation in blockchain systems is what are called relay networks, fast relay networks like Blockstore, Fiber, and Falcon. The main idea here is there's this network of fast relay nodes that are spread out throughout the world. And these set of nodes, they assist in spreading blocks very fast across the entire network. But there's a couple of issues with these relay networks. So one is if you look at how these relay nodes have to be interconnected to each other, that is again a topology design problem, and it's very difficult. And in today's solutions like fiber and block route, this interconnection is actually handcrafted. The second problem is centralization, because some of these relay networks, they are maintained by private parties. And this can lead to like censorship of blocks, which goes against the principle of a decentralized currency system. But nevertheless, even if such fast relay networks were to be present in the blockchain, in the Bitcoin network, Perigee discovers, or Perigee is able to adapt its topology in order to exploit the presence of such networks. So in this experiment, it's the same setting as before, like 1,000 nodes from bit nodes and so on. But the only change is we embed a network of 100 nodes in this setting. And these 100 nodes, they are interconnected to each other through high-speed links. And then we run Perigee as before. And basically, as shown in this picture, the gains achieved by Perigee are even greater here, because Perigee is able to realize the presence of this fast relay network, and it's able to adapt its topology to exploit the fast relay network. So, so in summary, I have presented Perigee, which is a simple lightweight algorithm for overlay construction, for peer-to-peer overlay construction in blockchain networks. Our protocol naturally adapts to network heterogeneities in latency, bandwidth, etc. Now, we believe this is there's like several interesting challenges that that have to be done for future work. For example, we have observed empirically through our simulations that Perigee actually converges to a protocol, to a topology. But it would be good to also theoretically analyze this protocol in order to understand the convergence behavior better. And we've also ignored security in our discussion. In Perigee, like a small percentage of neighbors, they are chosen randomly. And that should give some robustness to eclipse attacks, for example, in the same way that Bitcoin is robust to eclipse attacks. But again, like a more formal analysis of this is required. And third, we believe that the protocol should be able to adapt to changes in the network condition, to nurture and so on. But again, a more systematic analysis of this to see like how fast the protocol is able to adapt to such changes, that's also an interesting direction for future work. I'll conclude here, and this is the paper if you're interested. I'm happy to take questions.
Thank you so much. Please jump in with questions if you have them. I'm going to leave a reasonable time, but I'd prefer not to have long stretches of silence on the recording.
I can ask a quick question.
Okay.
So I'm just verifying basically. So the multi-armed bandit is, I'm assuming it's based on a multiplicative update rule.
So there are different candidate algorithms for the multi-armed bandit problem. Like there's the multiplicative weights, there is UCB, there's Thompson sampling, things like that. There is epsilon greedy, like this, like a huge array of algorithms for multiplicative weights, each having its own pros and cons. It's interesting to try all of them out and see which one works best. But in our work, we only looked at the UCB algorithm. we haven't really considered multiplicative weights or Thompson sampling and things like that.
Mm-hmm. Yeah, cool. That's very interesting. I'm only asking this because so we have our score function in the gossip sub, and which has a different objective than so it's more about protection, but also kind of to get some efficiency. But it would be interesting to try the multi-armed bandit as a substitute of our score function. So that's pretty cool. I'll take a look. By the way, does this paper have links to the various bandit algorithms?
No, it only has, I believe it has, I'm happy to share it with you also.
Okay, okay,
it points to like the main work or something. I don't know if it points to any type of a survey on bandit algorithms.
Okay, cool. Thanks.
There's a question in the chat here. Can you explain how the geography-based algorithm works?
The geography-based algorithm, so it works as follows. So basically in our experiments, we considered a degree bound of 8. So each node is interested in forming, is interested in connecting to 8 other neighbors. So in geography-based, we classify the nodes as belonging to one of 6 continents, like North America, South America, Africa, Europe, Oceania, Asia, things like that. And a node selects 4 neighbors randomly from other nodes within the same continent that the node belongs to. And if you're in North America, for example, you would select 4 neighbors within North America. And your other 4 neighbors are chosen randomly in other continents, like one in Europe, one in Asia, one in Oceania, and things like that.
Okay, thank you. So basically, I wanted to ask, because depending on the country of a node, maybe, you know, other nodes in the same continent have higher latency compared to nodes in neighboring continents. So for instance, a node in Marseille in France will have higher latency to a node in Russia compared to a node in Algeria, for instance. So yeah, but I understand. Thanks.
Okay.
Hello. Hi, it's Yanis.
Hi.
Hello. Very nice work. I actually have got many questions, but just to get to understand better. But just the basic one. By first of all, grouping the nodes is a very interesting idea. So one question I have about this is that if a node within a group of nodes is kind of less powerful or less well connected, then this is kind of, you know, becoming the weak link and is kind of holding everyone else back. Is that correct?
Yeah. Now that's true. So let's say we have. Let's say like the degree bound was 8.
Yeah.
Okay? And you're considering like subsets of size 5 or 6, let's say. Okay. Now let's say neighbors 1, 2, 3, and 4, they are very strongly connected, but neighbor 5 is the weakest link in this subset. Okay. Then basically a different subset is likely to have a better score compared to the subset that you're considering. So if you have 1, 2, 3, 4, 5, and 5 is the weakest link, then perhaps subset 1, 2, 3, 4, 6 might have a better score compared to subset 1, 2, 3, 4, 5.
Yeah.
So then this subset is now weeded out, and you would actually retain connection only to 1, 2, 3, 4, 6.
Okay, that makes sense. So my follow-up, my main question is the algorithm overall kind of promoting and is kind of favorable to mining pools, to groups of very strong nodes that can hash like?
I mean, our objective is essentially that. So our objective is we want to construct a topology such that you are as close to the rest of the miners as possible. And if it so happens that it's just this few mining pools that hold most of the hash power, then of course this protocol is going to attempt to establish strong connectivity just to these mining pool gateways
between those nodes. Okay, that's interesting. Okay, these are my questions. Thank you.
Okay.
Any other questions? Vitar? He's unmuting here. Give it a second.
Yeah. All right, got it. So I'm just to verify. So basically, if we use this algorithm as is, because it optimizes for the end objective, basically, I'm assuming that does open an attack vector. So if you want to put this in the wild, you probably have to regularize somehow, basically mix this end objective with some other objective that kind of essentially basically prevents things like eclipse attacks and whatnot. So you're going to end up having to get some trade-off between the end goal of performance, reaching the 90th percentile fast, and at the same time maintaining diversity in each neighborhood so that nodes that are maliciously good cannot just surround you.
Right. So if you do like 100% exploitation without any exploration at all, you can easily fall into this eclipse attack. But if you do 100% exploration, like in Bitcoin today, like completely random, no, like you're not like changing your neighborhood at all, then you tend to be safe. But for us, like there's some percentage of neighbors that you're exploiting based on how fast they are relaying, and there's some percentage of neighbors that you're choosing randomly. And this relative fraction between the two, it's going to it's like you said, it's going to decide how fast you're able to converge to a best solution versus how safe you are against like an eclipse attack. Yeah.
Cool.
But we haven't really looked into this problem in a very thorough, like a systematic way. But I believe like that's an interesting question for future research.
Cool.
Maybe one other part of that, or I think it probably also is part of the dynamics, is how you manage network topology and where concentrated hash power is changing over time. So how do you think about, caring more about recent results versus previous ones, expecting that topology changes?
Can you actually, like, I didn't fully understand the question.
So if there was a miner or a set of nodes that had a lot of power at the beginning of the network, can I end up with sort of outdated sense of which nodes I should stay connected to and are most important versus current?
So this process of scoring like subsets of neighbors and then retaining the best subset and then also connecting to like few random neighbors. So this process, it's not a one-time thing. This is going to be happening periodically. For example, you can imagine repeating this process every 100 blocks. I mean, depends on the exact blockchain system. But essentially this process is going to be continuous. It's going to keep repeating, right? So even if initially you discovered like some strong nodes and you made connections to them, but then over time, let's say their hash power became worse, then in subsequent rounds of this protocol, you are going to realize that their hash power has become worse, and therefore their score is going to degrade, and therefore you're going to be disconnecting from them. So this is not like a one-time thing where we do this, where we run this Perigee protocol and then we just don't do anything at all. Instead, this protocol is going to be continuously evaluating subsets of neighbors. So as the
you've got a fixed previous window of some number of blocks that you're computing this over, and that rolls forward.
So
and then the size of that and stuff like that is also going to be relevant to eclipse attacks and how responsive you are.
Yeah, the size of it is going to dictate how responsive you are to changes in the network conditions. But then if your window size is too little, then you don't get accurate estimation, like the then you don't have a whole lot of data on your neighbors, so you can't really accurately estimate how good or bad they are. But on the other hand, you would be able to track network changes much more fastly. But if your window is long, then you have more accuracy in terms of the quality of your neighbors, but then you're also slow to adapt to network changes. Yeah.
Do you have any benchmark values at all for these value, like things you played around with in simulation? And so what would you apply if you were to put that in a network model? Just out of curiosity,
benchmark models, as in like, I mean, our bench, do you mean like what do we compare the protocol against?
No. For this setting, so responsiveness versus being
okay.
to
I see. No, we haven't thought about this problem like in depth. There are like some theory works that try to analyze like these networks in the presence of churn. That would be like my starting point. I showed it in my slides also. Perhaps like they have some metrics on how to like quantitatively study like how fast you're able to adapt to changes.
Okay. Yep. Thank you.
Any other questions? We're right on the hour here. Last call. Excellent. Thank you so much, Shaileshh. I really appreciate it. Great to have you talk with us here. For those of you who are watching the recording on YouTube, please remember to like and subscribe. If you want to suggest a talk, you can find out how to do that in the description. And we'd love to have you go on our website, research.protocol.ai, drop your email address in the footer, and sign up to receive quarterly newsletters, announcements about these talks, as well as funding opportunity announcements. It's been great to have. Our next talk, apologies, let me pull it up here. Our next talk is Tuesday, September 8th at 1600 UTC from Dr. Gareth Tyson, Senior Lecturer at Queen Mary University. His talk title is Challenges in the Decentralized Web, the Mastodon Case, which is a paper that came out last year. Thanks for joining, everyone. We will see you next time.